Hey, welcome back to Math with Patrick. Today is November 18th, and we're solving problem 322 from the Daily Epsilon calendar. And the answer today should be 18 because that's today's date. So, we have a geometry diagram today. We need to find the product of the magnitudes of OA and OB. So OA is going to be this line segment right here, and OB is going to be that line segment right here. And supposedly, if we multiply these two lengths together, we do get the number 18. Now, something kind of interesting that I noticed about this diagram is that there are other line segment pairs that also multiply to 18. And they kind of follow this rule where we take some point on the nearer side of one circle and the far point on the other circle. So I'm just going to color code a few different kind of line segment pairs that I noticed also multiply to 18, and I'll also show that they do. All right, and this is the last one that we could just kind of compute by hand. And let's color code it. And let's start with that last one. So notice here how we have a 30, 60, 90 triangle. I guess it's kind of hard to spot, but this one right here is a 30, 60, 90 triangle. The reason why I know is because the short leg is half the hypotenuse right here. And I'm using those tick marks to help out, where this double tick mark shows me that this length is 3, and then the next double tick mark shows me that the same, or the other length is also 3. And so whenever we have a right triangle with a short leg, half the hypotenuse, we have a 30, 60, 90 triangle. The same thing is going to happen on the right side as well. And 30, 60, 90 triangles have this relationship where not only is there a quick way to multiply between the short leg and the hypotenuse, there's also a pretty quick method to multiply between the two legs. So I know that if I take this short length of 3, I can multiply it by root 3 to get this length here. So this kind of newer version of OB is going to be the length 3 root 3. And then we can kind of play the same game with the circle down here. Just this time our short length has a length of 2. So this length on that side has a length of 2 root 3. And then when we multiply these two lengths together, we get 6 times 3, which is 18. This will be true for that light green length as well, just kind of based on symmetry. Looking at that purple length, we have a length of 3, 6, and then 9, because this is another radius, another length of 3. We have 9 on top, and then we just have this 2 on bottom. 9 times 2, also 18. And then looking at the green length, this is the length of 3, and then we have 2, 4, and then 6, and then 3 times 6 also makes 18. So it seems like as long as we pick some kind of point on the near side of one circle and the far side of another, we'll always get 18 out of this product. And I want to show that that's true, and it doesn't matter what angle we have right here, or I guess right here, those would be the same angle. But it doesn't matter what that angle is, as long as we pass through that origin point, land on the near side of one circle, the far side of the other, multiply those two magnitudes of the line segments, we should always get 18. Let's start by just creating some variables. This is the length OB, but I am going to use this length in all my algebra, so I'm just going to call it capital B for now, not to be confused with the point. I think it would make sense to start making this right triangle right here. This can be our variable x, this can be our variable y. So we get this relationship that, or just like a Pythagorean theorem, essentially, that x squared plus y squared is equal to b squared. And I'm kind of like going back to what I know about parametric equations, where I think I want to, or both parametric, but also trig functions. I think instead of x and y, I want to express this in terms of like sine and cosine as well. And I want to pick either this angle right here or that angle right there. And those are going to be the same because they're alternate interior angles. It's the same thing as this angle down here because these are vertical angles. So I'm just going to assign, say, theta to be this angle right in there. And normally x is just equal to like some kind of magnitude. I guess that would be the b, and then times cosine of theta. Usually cosine and x are the ones that are related. But I'm noticing here, if I look at my right triangle more closely, here is my angle theta, again, because these two were alternate interior angles. If I think about what sine of theta is, sine is defined as opposite over hypotenuse. The opposite is my x right now, and the hypotenuse is b. So if I wanted to isolate x, I could multiply both sides by b, and I'm getting something a little bit backwards. Again, usually I'm used to x being related to the cosine function, but it looks like in this particular diagram, x is related to the sine function. And likewise, I could then prove that y is the same thing as b cosine theta. I guess I should square all of this. I'm distributing the square essentially. And then this is still all equal to b squared. And if I think about this in terms of like a trig identity, this makes sense to me because I could factor out ab squared, and then I'm left with that sine squared plus cosine squared identity, and this is just the number 1. Anyways, I'm not doing that though. What I'd rather do instead is think about some kind of equation that I could write for this circle and plug in, not all this squaring stuff, but rather plug in the fact that x is equal to b sine theta, and then y is equal to b cosine theta into some equation for this circle. Because if I do, then I'll be able to figure out how to get to that circle only by thinking about this variable theta. So again, thinking that this is the origin, we have a circle that is 6 units up, has a radius of 3. So I can write that as x squared plus y minus 6 squared equals 9. This is just kind of that standard circle formula. This minus 6 helps bring us up 6 units, and this number right here is always the radius squared. So now I can just plug in my b sine theta for x. I'll square it. I'll plug in my b cosine theta for y. I guess I can't square it just yet because of that minus 6. This is still all equal to 9. And my goal here is to strike some kind of relationship with b and theta. Again, because if I can get b to be just dependent on this theta, that's going to be nice because this is the same theta on the other side. And we can use that theta to relate it to this length of OA. So it looks like a quadratic to me. I think I should expand out my binomial here. We're going to get minus 12b cosine theta plus 36, still all equal to 9. And we still have this b squared sine squared theta at the start. I'm going to use that Pythagorean identity I mentioned earlier and just call this b squared. This will be minus 12 cosine theta b plus, maybe let's set it equal to 0, plus 27 equals 0. So now we do have a quadratic equation in terms of b. So I could use the quadratic formula to solve for b. It's going to be b is equal to, well, normally is x equal to negative b. B being this coefficient here, negative of this coefficient is just going to be a positive 12 cosine theta, plus or minus the square root of b squared, again b meaning this coefficient here. Squaring that, we get 144 cosine theta, minus 4ac. A is my leading coefficient, that's a 1. C is 27. 4 times 27 gives me 108, all over 2a. A, again, being this leading coefficient, it's just a 1, so I can go divide by 2. Let's simplify some stuff. We could just simplify the 12 and the 2 to get 6 cosine theta. And then, well, 144 is a square number, but 108 isn't. I know I could factor out a 4 from both. This would create a 36. This would create a 27. Oh, and then I guess I could factor out a 9 as well. And then so that would create a 4 and then a 3. And then I should probably hit both of these with a square root once they hop out of the square root sign. So I will get 3 times 2, which is 6. And then I will still have this square root of 4 cosine theta minus 3. actually this 6 should be a 2 because a 3 because I haven't divided it by that 2 yet. Okay, so I'm getting some kind of equation for our length of b in terms of theta, which is great. And this plus or minus, I think that just basically means whether or not we're on the far or the near side of our circle, right? Because this should always return a positive value because square roots always return positive values. So if I add a positive, I'm going a further distance. If I subtract a positive, I'm going a lesser distance. So I think this plus or minus represents the near versus far side of our circle. So let's do all that, hopefully a little bit quicker to solve for our length of A. Let's begin by writing the equation for the circle. This is going to be x squared plus y plus 4 squared. This plus 4 brings us 4 units down. And then equal to 4. That's this radius squared. X should still be related to sine instead of cosine, I believe. Here's the right triangle that I'm thinking of. This is my x distance. And then when I'm looking at this angle theta again, and I want to do opposite over hypotenuse, that's still sine. Sine is still with x. Okay, so x is going to be equal to, or b sine theta. I will square both of those. Y is going to be equal to b cosine theta. Add the 4, square that. This equals 4. And let's just do the same process, right, where we distributed this binomial right here. Oh, this is me remembering that I should have squared some stuff over here. That cosine should have been squared, as should that one. Then we have plus 8b cosine theta. That's going to be a 16, but subtracting the 4 over makes it a plus 12. Set that equal to 0. Still have this b squared sine squared theta. That will also combine to a b squared, again using that Pythagorean identity. We will have 8 cosine theta times b plus the 12 equals 0. And let's just Pythagorean theorem this. And I just realized I've been using b this whole time, but it should have been a. A is our hypotenuse. And instead of going back and erasing all those b's, I will just replace it here. A is equal to negative b, it's negative 8 cosine theta, plus or minus a square root of b squared, that's 64 cosine squared, didn't forget it, theta, minus 4ac, that'll just be 4 times 12, or 48, all over 2a. Then we, oh wait, should that be? Oh, that's kind of interesting. So earlier, we had a negative value or a negative sign in front of our b coefficient, and now it's plus. So I guess that's fine. That'll be negative 4 cosine theta, plus or minus. And then let's see, what kind of square numbers do we have in here? I think we could take out a 4 at least. That'll be 4, and then 16 and 12. Looks like we could take out another 4. It's going to be 16 on the outside, 4, and then 3. I'm noticing some similarity in the structure between these two, where we still get this 4 and this 3 as our coefficients on the inside. Plus or minus 4 root 4 cosine squared theta minus 3. And then wait, not a 4 because I haven't done the divide by 2. So now we have an expression for our a value. And again, A represents the magnitude of OA, and then B represents the magnitude of OB. So all I need to do, maybe it's not that easy, is multiply A by B. Before we do, though, I just noticed something a little concerning. It's just that I think this value is always going to be negative. I'm not quite sure, but I'm looking at this right here, and I feel like, okay, yeah, if I have a negative sign here and then I'm subtracting, this will always be negative. So my hunch here is that this negative plus that bit will still return overall a negative number. I think it has something to do with the fact that A is going down and to the left. Honestly, I'm not quite sure. But by removing that negative sign, I'm not really ruining anything because I still have the idea of a longer length and then a shorter length. So I believe this is fine, and I can multiply these two lengths and still get an answer for today. I tried looking, and I'm not really sure why this negative sign needs to go poof, but oh well. Maybe you can find it, and maybe you can tell me in the comments. Anyways, it is important though that these signs are different because a plus represents a further length and a minus represents a shorter length. And we did want to grab those sides or those kind of ending points from opposite sides of the short circle, right? A near one and a far one. So that just means that I'll make one of them a minus and one of them a plus. Let's just make A the one with a minus. Does that make sense? You know what? Let's make A the one with a plus, just because it is the further one in the diagram. So 4 cosine theta plus 2 root 4 cosine squared theta minus 3. And then we're multiplying this by 6 cosine theta minus 3 root 4 cosine squared theta minus 3. Okay, first times the first, we get 24 cosine squared theta. The outside term gives me minus 12 of this radical, and the inside term gives me plus 12 of the same radical. So conveniently, those complicated square root terms cancel. So I'm just left with the last, which is negative 6 times, and then the square root can release itself if we multiply it by the same thing. So times 4 cosine squared theta minus 3. We're almost there, right? Because we can distribute this negative 6 minus 24 cosine squared theta plus 18, bring down this 24 cosine squared theta, and almost by magic, but I guess not because it's all just math, these cosine terms go away, and we only get 18 for today. So it doesn't matter what the starting angle is. Like it could be, say, maybe negative 30 degrees to go to the left, or maybe it could be positive 30 degrees to go to the right. It could be 0. Those are the ones that we saw that were straight up and down. Doesn't matter what that theta is. We're always going to get 18 out of this product. So that's kind of cool. There is my solution. We just solved it generally, which does mean for whatever angle we have here, which is 15 degrees, that is, half of the 30, we're still going to get 18 because this product does not depend on that theta or that 15 degrees that we have in this diagram. So the magnitude of OA times the magnitude of OB is 18, and we can be all done. So thanks for watching, and I'll see you tomorrow. Bye.